Hello everyone, here is Khaled Omar, and in this video I'm going to demonstrate part 2 of the MPLS videos. So let's start. The content of this video will be focused only about MPLS VPNs. In the first video of the MPLS, we discussed the MPLS IP unicast forwarding, and in this video we are going to demonstrate only MPLS VPN, one of the most important MPLS applications. So let's make a review about the definitions that we used in the first video. We will start by defining the MPLS. What's MPLS? As we defined earlier, it's a routing technique that is used by service providers to connect an enterprise sites. If you have an enterprise with 4 sites, site A and site B, site C, and site D, and you want these 4 sites to be interconnected and connected to each others, you can use MPLS to connect these 4 sites through the MPLS cloud. But MPLS in its most basic form, MPLS unicast IP forwarding, is used to connect sites that belongs to only one enterprise. But if we want to add more enterprises or more customers, we will find a problem. So this problem we will demonstrate in the coming slides. So another definition, what is Mpls VPN? Actually, Mpls VPN is an application, and it is one of the most important applications of MPLS. This application can be used by service providers to connect multiple enterprise sites. What this means? It means that you can have more than one customer, let's say enterprise 1 or customer 1, and enterprise 2 or customer 2. Each enterprise has 2 sites, site A and site B for enterprise 1, and site A and site B for enterprise 2. We want to allow enterprise 1, site A and site B to be reachable and interconnected to each others, and we want enterprise 2, site A and site B to be interconnected to each others through the Mpls VPN cloud. Why we use the Mpls VPN? Because these 2 customers or these 2 enterprises may use overlapped private IP addresses. And this problem we are going to discuss in the coming slides, and we will show how Mpls VPN is going to solve this issue. So let's start discussing Mpls VPNs. First of all, as an introduction to Mpls VPNs, Mpls VPN is one of the most popular MPLS applications. There are many other applications for MPLS, like traffic engineering and other applications, but Mpls VPN is one of the most important and popular MPLS applications. Why? Because Mpls VPN is used to connect multiple customers or enterprise sites through the MPLS network or the MPLS cloud. So to understand MPLS, you must have a good background about MPLS unicast IP forwarding. Why? Because MPLS uses this MPLS unicast IP forwarding inside the service provider's network, with additional MPLS aware features at the edge between the service provider and the customer. Meaning at the edge means the provider edges. So what's the problem that appears when we try to connect multiple customers through the MPLS cloud? Of course, the duplicate private IP address range problems. The customers may use the same private IP addresses in the sites. So this can make problems. What are these problems? The MPLS routers will be confused. Which subnet or which prefix belongs to which customer? This many the service provider may use the MPLS cloud for a lot of customers. It can be possible that some of them uses the same private IP ranges inside their sites. So to discuss this problem, let's say that when connecting more than one customer or enterprise, usually I use the word enterprise that represents the customer. So when we try to connect more than one customer or enterprise through the service provider MPLS network, these enterprises could use the same private IP addresses inside their networks. Something possible. So if you try to support more than one customer using MPLS unicast IP forwarding alone, the MPLS router would be confused. Why? Because they will receive overlapped prefixes that belongs to each customer. So the provider edges will be confused which router belongs to which customer. If it chooses only the MPLS unicast IP forwarding. So to make this problem clear, we have here a service provider that uses MPLS inside its cloud. So we have MPLS cloud. This cloud consists of provider edge 1, provider 1, provider 2, and provider edge 2. We have here two enterprises, enterprise 1 and enterprise 2. Each has two sites. For enterprise 1, it has site A and site B. And for enterprise 2, we have site A and site B. For enterprise 1 site A, it uses a subnet private IPv4 prefix 192.168.1.0/24. And similarly for enterprise 2 site A, we just want to make the problem clear for you. Site A for enterprise 2 uses the same prefix 192.168.1.0. So without MPLS, using the normal MPLS unicast IP forwarding, this router will advertise this prefix, and this router will advertise this prefix. This one will be crazy. I receive two subnets from two different interfaces. Sorry. When it receives a packet destined to 192.168.1.0 subnet, it will not know which interface it should forward the packet out of, because there is a duplicate prefixes. Similarly for site B, for the two enterprises, let's start by enterprise 1. It uses subnet 10.3.3.0/24, and for enterprise 2 site B, it uses the same prefix as well, or the same subnet 10.3.3.0/24. When this advertises this subnet, and when this router advertises this subnet, provider edge 2 will be confused as well, and will store any of them. And when it receives a packet that is destined to 10.3.3.0, it will choose any of them, because it received two subnets from two different interfaces. So this is the problem. We call it duplicate private IP address ranges. So what's the solution for this problem? Because MPLS unicast IP forwarding cannot handle this issue, the solution is to use Mpls Vpn. Actually, in this slide, it describes that customer A uses networks 192.168.1.0/24 on site A, and 10.3.3.0/24 on side B. And similarly, customer B uses the network 192.168.1.0/24 on site A and 10.3.3.0/24 on site B. The first and most basic goal for a layer 3 MPLS VPN service is to allow customer A sites to communicate with customer A sites and only customer A sites. This is the goal that we want to do in this presentation. There are many other solutions, but we will discuss later. So to solve these duplicate private IP addresses between customer A and customer B, we will use Mpls VPN. And we will see how Mpls VPN is going to solve this duplicate private IP address ranges problem. So the first thing that we are going to define here that is part of the Mpls VPN mechanism is called virtual routing and forwarding, VRF. Actually, VRF is a table, is a routing table. But what is the difference between VRF and the global routing table or the routing information base that the router uses? VRF tables are multiple routing tables as a definition for the VRF, by the way. VRF are multiple routing tables used by Mpls VPN for each customer. So Mpls routers will use multiple routing tables called virtual routing and forwarding tables or VRF tables and dedicate each table for specific customer. So these VRF tables separates customer routes to avoid the duplicate IP address ranges problem. Each customer will have a separate VRF. Actually, both the provider and provider edge routers run LDP, Label Distribution Protocol, and an IGP, whether it's EIGRP or OSPF, to support unicast IP routing, as in Mpls unicast IP forwarding. We discussed this in the first video, part 1. However, the IGP advertises routes only for subnets inside the Mpls network with no customer routes included. What this means? It means that the IGP is used inside the Mpls cloud of the service provider, and as a result of this, the provider and provider edge routers can together forward label packets from the ingress PE to the egress BE. But the IGP is not learning routes from customers. So, to separate the learned customer routes, BE routers don't store the routes in the normal IP routing table, which routes, customer routes, but they instead store those routes in separate pair customer routing tables. And these tables are called the VRF tables. Then, after the provider edge routers store the learned routes from each customer on its specific VRF table dedicated for this customer, the provider edges uses BGP to exchange these customer routes with other provider edges and never advertises the routes to the PE routers. So provider routers don't have any learning routes for customer routes or customer prefixes. Only provider edges uses BGP to learn those routes. And we will learn in the coming slides how provider edges are going to learn those routes. So the extra work for the PE routers relates to the fact that Mpls VPN data plane causes the ingress PE to place two labels. We call it label stack on the IP packet as follows. The first label, we call it an outer MPLS header or label. Actually, it is header, not label only. And as you know, the MPLS header consists of four fields: the label, the EXP that's used for quality of service, the bottom of a stack, the S bit, it's 1 bit only and used as a flag, and the TTL. So Mpls VPN data plane uses an outer MPLS label or header with a label value that causes the packet to be label switched to the egress PE. So if we will consider that we have an IP packet, MPLS add two labels. We call this outer label and we call this inner label. Actually, this is a header, MPLS header, of course with label field, and this is an MPLS header with label field. The S bit here is set to 0. The S bit here is set to 1. So the inner MPLS header with S bit equal 1 with a label value that identifies the egress VRF table, or the interface that will be used by the egress provider edge to send the packet unlabeled out of this interface through this VRF table. More details will come next. This is something like an overview. I just want to show you that Mpls VPN is not like the Mpls unicast IP forwarding, where Mpls unicast IP forwarding used only one label, one header, Mpls header, but Mpls VPN uses two Mpls headers. This is the outer and this is the inner. So an overview of the Mpls VPN data plane. We will consider that we have two sites belongs to enterprise 1, site A and site B, and host A inside site A needs to communicate with host B inside site B. The circles represent the steps that we are going to discuss. First, host A will send an unlabeled packet to customer edge 1. We call it customer edge 1 for site A, and this is customer edge 1 for site B. So CE1-A will receive an unlabeled packet. So what should it do? It should do the normal routing based on the destination IP prefix and based on the routing table at CE1-1-A. Once it decides that it should forward the packet out of this interface, it will send an unlabeled packet because, as we discussed before in the first video, the customer edge routers has no awareness of MPLS. So BE1, provider edge 1, will receive an unlabeled packet on interface serial 2/0, and this interface is associated with VRF1, a separate routing table. Routing table that is dedicated for enterprise 1. More details will come in the next slides, but let's think that it will not, BE1 will not store, this is not an update, this is the packet that needs to be forwarded. So BE1 will check VRF1 What is inside VRF1? It will check the CEF forwarding information base and decide that the packet should be forwarded out of this interface. And before forwarding the packet, it should add two labels, outer label and inner label. Outer label with label 10 and inner label with label 17. And then send the packet, the labeled packet, out of this interface. Now B1, provider edge 1, will receive a labeled packet. So what it will do, it will check its MPLS label forwarding information base and decide that it should swap the outer label from 10 to 15, and it will not do anything to the VPN or the inner label, because P1 don't have information about don't take action about regarding the inner label. It just checks the header with flag set to 0 and take the action, which is swap from 10 to 15, and then check the output interface, let's say this interface, and send the labeled packet after swapping the outer label from 10 to 15. Now BE2, provider edge 2, will receive a labeled packet with two labels. What it should do, at the moment, it will do two lookups, one for the outer label and one for the inner label from its MPLS label forwarding information base. And once it decides that the action is to remove this label and remove this label and forward a unlabeled packet in step 5 out of serial 2/2 destined to customer edge 1-P. And normally customer edge 1-P will receive an unlabeled packet, and it will use its normal routing table and forward the packet to host B. Actually, this is an overview. There are no details discussed in this slide. This is an overview of the Mpls VPN data plane. It just shows you that Mpls VPN is not like Mpls IP unicast IP forwarding. The difference is here it uses two labels, inner label and outer label. Provider routers take action based on the outer label, and the egress provider edge router take action based on the inner and outer labels. And as mentioned here, the yellow square is the outer label, we call it LDB label, and the green square is the inner label, we call it VPN label. So let's have an overview about the Mpls VPN control plane. So Mpls VPN's control plane uses three new concepts. Actually, we discussed a little bit about the first one, which is VRF tables, virtual routing and forwarding tables. And inside these VRFs, we will use new concept called route distinguishers and another concept called route targets. These three concepts represent the Mpls VPN control plane, and we will discuss each one of these in details in the coming slides. what is VRF tables, what are the route distinguishers and what they are used for, what are the route targets, and how to represent the RD and RT and what they are used for. So we will start here in this slide discussing the first element or the first concept of the Mpls VPN control plane, which is the VRF tables, virtual routing and forwarding tables. As we defined VRF table earlier, VRF table exists inside a single MPLS provider edge. There are no VRF tables inside the provider, like P1 in the previous slide. So provider edges requires at least one VRF for each customer attached to that particular router. When we saw that customer edge 1-A router connected to provider edge 1, this provider edge 1 router requires at least one VRF table dedicated or attached to this customer, dedicated for this customer, and at least one. We can use more, but we will only choose one in this demonstration. So each VRF has two main concepts. What are the concepts of the VRF? It has an IP routing table called rep, like the normal routing table, and it uses a safe forwarding information base populated based on that VRF's rep, because you know the safe forwarding information base comes from the routing information base. So the VRF has these components, the rep and the safe FIP. Let's see here from provider edge 2 point of view, where it is connected to two enterprises, enterprise 1 and enterprise 2, side B for enterprise 1 and side B for enterprise 2. As we can see, there is a routing protocol used between this customer edge router and this provider edge router. Similarly, for enterprise 2, there is a routing protocol used between customer edge 2-B and the provider edge router. This routing protocol can be an IGP or BGP. In this presentation, we will discuss only IGP, and we will use EIGRP just to advertise this subnet from this site, from this router to the provider edge through EIGRP. Someone will ask why we will use EIGRP if this is in autonomous system and BE2 is in a different autonomous system. Actually, Mpls VPN will use an instance inside BE2 that is dedicated for this autonomous system, let's say 100, that is used by enterprise 1. So there will be an instance here, we call it address family, for autonomous system 100. So it will allow neighborship between BE2 and CE1B EIGRP neighborship to advertise routes through EIGRP. And this prefix or this subnet will not be stored in the global routing table at BE2. It will be stored in the VRF dedicated for enterprise 1 that is associated with this interface serial 2/2. So when enterprise 1 customer edge 1-B router advertises this subnet and BE2 learns about it, it will add this route to the dedicated VRF, which called VRF1 for Enterprise 1, with next hop 80.1.1.1, this next hop, and output interface serial 2/2. Similarly, for Enterprise 2, CE2-P will have EIGRP neighborship with provider edge 2, and there will be an instance of EIGRP dedicated for sub ASN or autonomous system number 300, if we will consider that this Enterprise 2 in autonomous system 300. So there will be EIGRP neighborship between CE2-B and provider edge 2, not an EIGRP neighborship between the EIGRP used inside the service provider autonomous system, because this will not happen. The provider network uses, let's say, autonomous system 200, and this customer site or enterprise uses autonomous system 300. And one of the requirement of EIGRP is that the two neighborship routers should have the same autonomous system number. So for Mpls Vpn, when we are going to use IGP between the provider edge router and the customer edge router, we will use an instance that defines the autonomous system for each customer to perform EIGRP neighborship and exchange and learn the routes through this neighborship, through the update messages. So when this customer edge advertises this prefix, when BE2 receives this update from this interface serial 2/3, it will add this route to the dedicated VRF for Enterprise 2, which is called VRF2. As you can see, the two prefixes learned by provider edge 2 are the same, 10.3.3.0/24, but each one is stored in a dedicated or a specific VRF table. Here VRF1 for Enterprise 1, and here VRF2 for Enterprise 2. And the next hop IPs are different. This 80.1.1.1 represent the customer edge for Enterprise 1 side B, and this 90.1.1.1 next hop represents the IP address of the customer edge router of Enterprise 2 side B. And for sure, the output interfaces are different, and when PE2 will receive a packet destined to 10.3.3.0, actually it will use labels. So we are not going to discuss this right now. I just want to tell you that each subnet or prefix learned by each customer will be stored in a specific VRF table. This is how VRF works. Serial 2/2 is associated with a VRF, which is VRF1, and serial 2/3 sorry, is associated with VRF2. And BE2 will have two different VRF tables, each one for each customer. This is to separate between the learned routes if they are duplicated from two customers. The second concept or the second element that Mpls VPN's control plane uses are called route distinguishers. And route distinguishers works with multi-protocol BGP. How this will work, we are going to discuss in this slide. And what are the usage of the root distinguishers, we will discuss here. Actually, Mpls Vpns deals with the overlapping prefixes problem by adding another number, because as you can see, it received from CE1-P 10.3.3.0/24, and it received from customer edge 1-P, customer edge 2-P 10.3.3.0/24. The VRF, yes, separates these two learned routes, but when these two learned routes will be redistributed in BGP that the MPLS cloud uses, they will be the same. So here we will use the root distinguishers. So what is the purpose of the root distinguisher? Is a number called root distinguishers used to be added to the prefix and to differentiate, to make this prefix unique. And this new form will be called the new network layer reachability information, or NLRI. Actually, each root distinguisher can represent a different customer, or maybe the same customer sites uses the same uses the same or different root distinguisher. It doesn't matter, because when this provider edge router is going to redistribute the EIGRP learned routes into BGP, it will assign a root distinguisher for this prefix to make it unique, and it will assign another root distinguisher for this prefix to make it unique. Of course, the root distinguisher used for VRF1 shouldn't be the same as the root distinguisher used for customer 2 or enterprise 2 or VRF2, because if we will use the same, which will not be allowed in the iOS, it doesn't make any sense, because if we use the same RD here, root distinguisher, for this VRF, and the same root distinguisher for another VRF, and two duplicated prefixes will be received, there will be no difference. Still, there is duplication. So RD's root distinguishers for each VRF shouldn't be the same to make the NLRI value unique. And so what is the new NLRI value? We will discuss the format in the last point here. So as we said, the RD values may or may not be the same for the same customer or enterprise, because BE1 will use VRF1 for customer 1 site B, and BE1 is also connected to customer edge that belongs to enterprise 1, so it will have a VRF dedicated for this customer. The root distinguisher value that will be used inside the VRF on BE1 may or may not be the same as the root distinguisher value used in the VRF of customer 1 stored in BE2. But usually, we use the same root distinguisher for the same customer. Why we use this root distinguisher? Root distinguishers allow BGP to advertise and distinguish between duplicate IPv4 prefixes. So this is the main function, or the main purpose of root distinguisher, is to advertise and distinguish between, to distinguish actually, advertise by BGP, but to let BGP or allow BGP advertise and distinguish between the duplicate IPv4 prefixes. So the concept is simple, which is advertise each network layer reachability information or prefix as the traditional IPv4 prefix, but add another number, which is the root distinguisher, that uniquely identifies the root. And this new format of the network layer reachability information will be called VPN v4, and it has two parts as we discussed here. The first part is a 64-bit dedicated for the root distinguisher value, and the second part represents the 32-bit IPv4 prefix. So the new network layer reachability information will be like that: the IP prefix and the root distinguisher. Why to use root distinguisher? To distinguish between duplicate IPv4 prefixes. So BGP can differentiate between duplicate prefixes. The RD is 64-bit, the IP prefix is 32-bit. Let's see how RDs works with multi-protocol BGP. As we mentioned, by the way, this is inside the gray square is inside represents provider edge 2. As we mentioned, it learned about 10.3.3.0 from customer 1 site B, and it stored this information inside VRF1 that has a root distinguisher value 100:80, and we will see how the format of the root distinguisher in the coming or the next slide. But the IGB don't know about the learned the IGB stores the learned root or prefix inside the dedicated VRF, let's say VRF1, because the provider is connected to, provider H2 is connected to customer 1 site B through interface serial 2/2, which is assigned or dedicated for or attached to VRF1. We will see this in the configuration. So any routes, any learned routes by the IGB will be stored in this VRF. That's why 10.3.3.0/24 came in VRF1. And similarly, 10.3.3.0 from Enterprise 2 came in VRF2 by the IGB. Actually, this instance of IGB should redistribute these learned routes inside BGP. So this learned route should be redistributed into BGP. Now BGP will have two routes with the same prefix or NLRI. So that's why we use the new format with MBBGP, which is the root distinguisher and the IP prefix. As you can see in the BGP table, the two learned routes are unique because of the used root distinguisher, and this is the purpose of the root distinguisher, to distinguish between duplicate prefixes. If you will use this NLRI as a whole, it will not be the same as this one. Then, regardless of these details, we are just discussing root distinguishers. This BGP table will be advertised through iBGP to BE1. because there is something called VPN v4 between BE2 and BE1. We will discuss this in the next or in the coming slides. But all what you should do or what you should know is that root distinguishers with multi-protocol BGP are used to distinguish between duplicate IP prefixes. So as you can see, the BGP table received by PE1 has this new NLRI format, and these two new prefixes are unique. They are not duplicated. This is the purpose of the root distinguishers. So what is the root distinguisher? We are talking about the format, the number of bits, etc. As we mentioned, every VRF must be configured with a root distinguisher. Why? To distinguish between duplicate IP prefixes. So the length of the RD field or number is 8 bytes, 64 bits, with some required formatting conventions. The first 2 bytes, or 16-bit, should be the autonomous system number. Actually, it can be an IP address, but I use it the first preferred term, which is the autonomous system number. So the first 2 bytes are the autonomous system number, and the second 6 bytes can be any integer value you want. So the RD format is as follows: autonomous system number and any numeric value or integer value you want to use. Let's say that we are configuring VRF1, and as we said here, every VRF must be configured with a root distinguisher. So inside this VRF, we will use root distinguisher. As we know that VRF1 belongs to customer 1 or enterprise 1. So the autonomous system used by enterprise 1 is 100. And we write type a column, and we will use any integer value, whatever you want. Let's say 80. So this root distinguisher will be used to distinguish between, to allow BGP to distinguish between duplicate IPv4 prefixes. And similarly for VRF2, configured on provider edge 2, must be configured with a root distinguisher. Let's say 300, the autonomous system number of enterprise 2, colon, and let's say 90. We can use 80, whatever, because the autonomous system number, that's why I prefer the autonomous system number, makes the root distinguisher unique. Even if you use the same integer value for the second 6 bytes. This is 300 colon 80, and this is 100 colon 80. Still unique numbers. So all what you should know in this discussion is that every VRF must be configured with a root distinguisher, and this is how the root distinguisher looks like, the format. The next slides describes how provider edge 1 then it chooses the VRF into which to add the learned routes by BGP based on the concept of root target. And this is the third element or the third concept that the Mpls VPN control plane uses. Now we discussed VRF, and we discussed root distinguisher. Next, we will discuss the concept, the third concept, which is root target. So the third concept or the third element that Mpls Vpn control plane uses is the root targets, and it is used with multi-protocol BGP. The purpose of the root targets is to enable MPLS to support all sorts of complex VPN technologies or VPN networks. But in this demonstration, we will focus only about two customers. Each customer has two sites. Each customer needs its sites to be reachable or connected to each other and only to this customer. So site A for customer 1 should be interconnected to site B for customer 1 and only for customer 1. And site A for customer 2 should be interconnected to site B of customer 2 and only sites for the same customer. We don't want to use a scenario like, let's say here, a shared network or site that belongs to customer 3, for example, and we want one of these sites, let's say site A of customer 1, should learn routes and advertise routes to this customer. This can be achieved by the route targets. But in this demonstration, we are not going to use this scenario. We will just want to routes here from this site be added. I'm talking about the provider edges. Routes learned from this provider edge 2 should be stored in the VRF dedicated for customer 1 inside provider edge 1. So how the learned routes by BGP and the advertised routes by BGP, one will be stored in VRF1 and another one will be stored in VRF2. This is based on the route distinguisher, the route target, sorry. This is the purpose of the route target. So route distinguisher is used to distinguish between duplicate IPv4 prefixes. Route targets are used to store the prefixes inside the correct VRF. For example, route targets allow some sites to be reachable from multiple VPNs, as we discussed here, but we will not demonstrate this in this video. So provider edges advertises route targets in BGP updates as BGP extended community path attribute. As all of you know, BGP uses a path attribute called BGP extended community. This path attribute will be used by Mpls Vpn for the route target. So BGP extended community path attribute are 8 bytes in length with the flexibility to be used for a wide variety of purposes. But in this demonstration, in this video, when we are discussing Mpls Vpn, we will find out that Mpls Vpn defines the use of the BGP extended community path attribute to include one or more route target values. So what are the route targets? In particular, its format. The route target format is similarly as the route distinguisher. It looks the same. As we mentioned in the previous slides, the extended community path attribute is 8 bytes and the route distinguisher is 8 bytes. So the route target as well is 8 bytes, and it uses the same format as the route distinguisher. Autonomous system number in the first 2 bytes and an integer value in the second 6 bytes. However, a particular prefix can have only one root distinguisher. That same prefix can have one or more root targets assigned to it. And we will learn how root targets are configured and used in the coming slides. So the concept of the root target is MPLS uses root targets to determine into which VRF a provider edge should store the iBGP learned routes. As we discussed in the previous slides, BE2 advertised to BE1 via BGP, and here we used iBGP, the two learned routes. So BE1 now learned via BGP two prefixes. They are unique because of the root distinguisher, so it can distinguish between them, but BE1 don't know which route should go to which VRF. This will be accomplished using the root target. So the purpose of the root target is to determine into which VRF a provider edge should store the iBGP learned routes. Because of the root target configured on VRF1 on B provider edge 2, BE1 will decide that this specific prefix will be in VRF, let's say 1 as well, on provider edge 1, and the second prefix that come from customer 2 side B will go to VRF2 because of the configured root target in VRF2 inside provider edge 2. Root target tells the provider edges which route should be added to each VRF, as we discussed here. So root targets provide the ability to allow some sites to be reachable from multiple VPNs, and we will not discuss it here just for simplicity. But if you will learn the concept, you can do whatever scenario you want to use. And this is how root targets are used with multi-protocol BGP. So to make it clear and understandable for you, let's repeat the same example. Let's repeat the same example, but we will add the field root target here to let you understand the purpose of the root target. As we mentioned, BE2 has VRF1 for customer 1 side for customer 1 and VRF2 for customer 2. VRF1 is configured with root distinguisher 10.80 to distinguish between duplicate IPv4 prefixes with other customers, and VRF2 uses root distinguisher 300:100. Now VRF1 is configured with export root target, and we will see the difference between export and import root target. But here we are using export root target 100:20. What this means? Export means when you advertise from IGP into BGP, as you can see here. So this is the export root target. And inside BE1, it has VRF1 with root distinguisher 100.70 and import root target 120. This export, this prefix that will be redistributed into BGP and added to the Bgp table will have the export root target associated with the Bgp entry. This is how multi-protocol Bgp works. It adds the new NLRI to make the prefix unique and attach the export root target to this learned prefix. And similarly for site 2 or enterprise 2 site B, the redistribution from the IGB into BGP will take the prefix, add it to it the root distinguisher, add it to the Bgp table, attach the export root target to the Bgp table. This is the direction of advertisement from BE2 to B1. Now BE2 send the Bgp table via IBBGP to BE1. Now BE1 received this table and it will redistribute what is inside BGP into IGP. But which one entry will be distributed to which VRF based on the root target. The root target came with this new IP prefix. It will check the import root target inside VRF1. Once they are the same, this entry will be added to this VRF. Similarly, this root target, which was their export, will be compared to the import root target value inside provider edge 1 VRF2. If they are the same, then this root, this IP prefix, will be redistributed inside this VRF2 because of the import root target is similar to the export root target came with the BGP update. This is how root target works. If, for example, we set this root target to 170, so when we redistribute from IGP to BGP, the learned root will be like this, root distinguisher and the prefix, but the root target will be 70. So when this BGP table will be received by provider edge 1, which is 100, the root target 170, the export root target here, provider edge 1 want to redistribute this learned prefix into a specific VRF. It will check the import root targets on each VRF. Which one I should redistribute this prefix into to this VRF? No, the import root target here is 100:20. And for VRF2, the import root target 330, not the same. So neither to this prefix will neither be redistributed into VRF1 nor VRF2, only if this value matches one of the import root target configured inside a VRF. So when you configure a VRF, you give it a name. Let's say we are configuring on provider edge 2, and inside the VRF subcommand, you configure the root distinguisher, which is 100:80 as used in this example, and you configure root target export for routes going to another provider edge. Let's say the value 100:20, and you configure as well route target import. Let's say it is 100:20. If provider edge 1 will advertise to provider edge 2 a route in VRF1 that has export route target 100:20, this specific prefix will be stored in VRF1 because of the import route target matches the export route target on provider edge 1. So this is how route targets works. So as a summary, to define the export, meaning it means to redistribute out of the VRF into BGP, and import means to redistribute into VRF from BGP. And each VRF needs to export and import at least one route target. The previous example shows only one direction, which is from BE2 to BE1, which is exporting on the right BE2 and importing on the left BE1. However, BE2 needs to know the routes for the subnets connected to Enterprise 1 Customer Edge 1 Site A and Enterprise 2 Customer Edge 2 Site A as well, who were in the left. So BE1 needs to learn those routes from the customer edges, redistribute them into BGP with some exported route target values, and advertise them to provider edge 2 using iBGP, and then provider edge 2 import the correct routes based on provider edge 2 to import route targets into provider edge 2 corresponding VRF. So if from BE2 to BE1, export here should match import here. So the route from VRF1 should be stored in VRF1 on BE1. And similarly, the export route target value on VRF1 on BE1 should match the import value on VRF1 on provider edge 2. So the learned routes on VRF1 will be stored on VRF1 on BE2. It's that simple. So for simple Mpls VPN implementation, where VPN consists of all sites for a single customer, and this is what we are going to discuss here in this video, most configuration simply use a single route target value, with each VRF for a customer both importing and exporting that route target value. Maybe I will not use this recommendation. I did this recommendation, but I will not use it. I will use different export and import values for, I mean that if I used export value here, I should use the same import value here. But I will not use the same export value here as this one, but I must use the same import value as this one. This export may or may not be as this one used here in VRF1. This is a note. The previous example that we used in the previous slide show a different numbers for the root distinguisher and root target values so that it's clear what each number represents. But in practice, you can set a VRF's root distinguisher and one of its root targets to the same value, but it depends on your scenario. You can use the RD, let's for example say BE2. We are configuring VRF1. We can configure the root distinguisher and one of the root targets, or both, the export and import, same as the root distinguisher. If we are going to connect the same sites for the same customer only, we can use the RD value as the RT import and export values. But in the example at the end of this demonstration, I will not use this, just to make you understand what is the purpose of each one of them. What is the root distinguisher and what is the root target, and which values will be configured for each one of them inside provider edge 2 and provider edge 1 and VRF1 and VRF2. Now we finished the Mpls Vpn control plane. In this slide, we are going to discuss the Mpls Vpn data plane. And the data plane here consists of two tables or two elements. The first element is the Ceph forwarding information base, and the second element is the Mpls label forwarding information base. Let's recall the example that we used when we discussed the overview of the Mpls Vpn data plane, where host A in enterprise 1 site A want to communicate with host B in enterprise 1 site B. Host A will send an unlabeled packet to the customer edge, and the customer edge will use the traditional and the normal routing decision based on the destination IP address and the routing, the entry inside the routing table that matched this prefix. So once it decides that it should forward out of this interface an unlabeled packet because it has no awareness of MPLS, this unlabeled packet will be received by the provider edge 1. Provider edge 1 actually has serial 2/0 connected to the customer edge, and it is attached to VRF1. But let's think about how provider edge 1 will react. It received an unlabeled packet. Which table it should check? It should check the Ceph FIP. But because of we are configuring Mpls Vpn, and this unlabeled packet came from an interface that belongs to a specific VRF, provider edge 1 will check the Ceph forwarding information base for VRF1. Because there is another Ceph forwarding information base for VRF2, which has the same prefix. So VRF provider edge 1 will not check VRF2 because of the configuration of VRF1 associated to serial 2/0. So it will check the Ceph forwarding information base of VRF1. Now it will find an entry matching the destination IP address inside the packet, and an out label 10 and 17. What is this 10? This should be the outer label, and what is this 17 should be the inner label. So immediately BE1 will add a label to the packet, the outer label 10, and an inner label 17 in step number 3. And these labels will be attached to the IP packet. and this packet will go outside of serial to 1, destined to provider 1. Now provider 1 will receive a labeled packet with two labels. P1 will check the outer label because it is not configured with VRF concept or things like what MPLS uses. It's configured normally as MPLS unicast IP forwarding. So it will only realize and understand the outer label. What should it do when an MPLS router receives a labeled IP packet? It should check the MPLS label forwarding information base. Once it finds a matching label for the outer label, it will take an action. What is the action? If the out label has a value, then it means swap. Swap 10 to 15. And then what? Send the packet out of interface serial 2/0. Now B1 will send the packet outside of this interface with the two labels, the outer label and the inner label remains the same. Only the outer label is changed by provider 1 because this inner label or the VPN label is dedicated for usage or checking by the provider edge, the egress provider edge. Now BE2 will receive a labeled packet with two labels, and this provider edge will check its MPLS label forwarding information base. First, it will check for an entry for the outer label. Action, no out label means Bob. So it will decide to remove this label. Out interface is not available. Then it will check the inner label or the VPN label inside the MPLS label forwarding information base. Once it finds a matching entry, it will check the out label. Not available means Bob or remove the inner label and send the unlabeled packet out of serial 2/2. Actually, the job of provider edge 2 router that makes two lookups for the two labels will be modified by the Penultimate Hop Popping, PHP, and we will demonstrate this at the end of this presentation. To let provider edge 1 remove this label, the outer label, and to let BE2 do only one lookup, and this lookup will be on the VPN label. This is something like an overview. We don't know how the MPLS label forwarding information base are constructed and how the safe forwarding information base is constructed. But this is how Mpls Vpn data plane works. The egress provider edge at the moment do two lookups, one for the outer label and one for the inner label, and provider routers only do lookups on the outer label. Now provider edge 2 will decide that it should forward an unlabeled packet out of serial 2/2 to the customer edge, and then the customer edge will send the unlabeled packet to host B. So let's first know about the MPLS label forwarding information base and the VPN label or the inner label. Let's back to our example where provider edge 2 is connected to enterprise 1 side B and enterprise 2 side B. Customer edge 1 of side B for enterprise 1 advertised this prefix via EIGRB, and BE2 stored this learned route inside VRF1 because of this interface is associated with VRF1. In MPLS IP unicast IP forwarding, when a provider edge learns a route for a specific prefix, it immediately assigns it a local label. But the label that will be assigned by the provider edge will be the inner label, the VPN label. Let's say that BE2 assigned a label 17 for this prefix in VRF1, and for this prefix that came inside VRF2 from enterprise 2 side B, assigned it an inner label 19. These labels are the VPN labels that will be used in the inner header or the inner label. And these entries, BE2 will add it to its MPLS label forwarding information base. There is an MPLS label forwarding information base for each VRF, and you can show the complete MPLS label forwarding information base, and it will show that a label 17 assigned to VRF1 prefix 10.3.3.0 and a label 19 assigned to prefix 10.3.3.0 for VRF2. And this is the contents of the MPLS label forwarding information base in label without any out label. And the next hop, it means that if BE2 will receive a labeled packet and the inner label is 17, the action will be to remove the label. Similarly, if BE2 received a labeled packet with inner label 19, the action will be remove the label and send the packet to this next hop for label 17 in the inner label out of interface serial 2/2 to customer E1, customer edge 1 dash B. And similarly for label number 19. The next step is that the MPLS label forwarding information base will feed the Bgp table, because the Bgp table, the multi-protocol Bgp, has an LRI, which came by the route distinguisher for the specific VRF and the IP prefix, and the export route target, and now the inner label or the VPN label. When you redistribute from the IGP inside BGP, this is how the BGP table will be constructed, and its elements will be given or will be taken from this from the VRF, this from the VRF, this from the MPLS label forwarding information base of that VRF. And the next hop will be the same router because it is redistribution. And this is the router ID of BE2. And then BE2 will use the VPN v4 between BE2 and BE1 and will advertise this BGP table via IBGP to BE1. As we mentioned here, the labels assigned by BE2 to the learned prefixes are VPN labels or inner labels. In MPLS unicast IP forwarding, because BE2 was learning a prefix from the customer edge router, and it is not stored inside a VRF, it automatically assigns a local label to this prefix and advertise this prefix or this label IP prefix binding using LDP to the other LDP neighbors. But because of we are using Mpls VPN, and this prefix will be stored inside a VRF, a specific VRF, the local label that will be assigned to this learned prefix will be a VPN or inner label. In this slide, we will discuss how the outer label is added and redistributed or advertised. BE2 is configured with a Bgp ID and label ID 4.4.4.4, and there is a VPN v4 between, this is configured by the way, configured between BE2 and BE1. So BGP will advertise routes from learned at BE2 from BE2 to BE1, and BE1 will advertise learned routes via BGP to BE2. But what is the next hop for BE1 and BE2? For BE1, the VPN neighbor is 4.4.4.4. For BE2, the VPN neighbor is 1.1.1.1. BE2 will not advertise the learned prefixes and the labels via LDP. Why? Because they are stored in VRF, and this is for Mpls VPN. They should be advertised via IBGP through the VPN between BE1 and BE2. But because we are advertising subnet 4.4.4.4/32 using IGP, now the normal LDP will assign this prefix and a label, and this label will be the outer label for the packet. And then BE2 has LDP neighborship with B1 and B2. So this prefix will be assigned a local label by BE2, which is 15, let's say 15, and advertised to B1 and to B2. Not only this prefix will be assigned a label and advertised by LDP, but all the networks associated to BE2 that will be advertised by the IGP inside the MPLS cloud will be assigned a label, so provider edges can forward MPLS packets, the labeled packets based on the outer label. And because of B1 and B2 has no awareness of Mpls VPN, but they are aware of Mpls normally, they will check only the outer label with the flag set to 0. So when B1 and B2 receives a packet, a labeled packet, it will check only the outer label. BE2 has Mpls VPN configured with P1. It can checks both the inner and outer labels. For BE1 label information base, for only this specific prefix. Why we choose this prefix? Because this one will be used for the VPN between BE2 and BE1. So when BE2 is advertising to BE1, it will use this prefix or IP. Similarly, when BE1 is advertising through BGP, through the VPN to BE2, it will use this next hop. This will be in the next hop. So we will check the labels for this prefix only in this slide. Here, P1 received an update from BE2 for IP prefix 4.4.4.4/32 with label 15. Normally, P1 will assign this prefix a local label, which is 10, and advertise this update to the other LDP neighbors. Similarly, with B2, it will assign a local label, let's say 20, to this IP prefix and advertise to the other LDP neighbors. Now BE1, provider edge 1, will receive 2 LDP updates for the same prefix with 2 labels. It will store these 2 labels in the label information base data structure and choose the best one of them based on the routing protocol, the IGP used inside the MPLS. And then it will update the MPLS label forwarding information base for BE1 and the CEF forwarding information base. So we discussed how BE2 constructed its MPLS label forwarding information base. What about BE1? Because we are working in this direction from BE2 to BE1. First thing that BE1 will receive from the VPN v4 neighbor BE2 will be the Bgp table. And this will come from either RP1, this BGP update will come either from B1 or B2. Even there is a VPN between BE1 and BE2. So eventually the Bgp table will be received by BE1 in this format with 2 entries, one for this prefix or NLRI, new format, and one for this entry with root target configured as export root target on BE2 and the VPN label assigned by BE2 for the learned prefixes that are stored inside the VRF. And the next hop here will be neither B1 or B2, will be the VPN v4 neighbor, which is BE2. Now this entry, this Bgp table, should be redistributed into the IGP. but BE1 uses VRFs. So which entry should go to which VRF based on the root target? Because this VRF inside BE1, by the way, all these things are inside BE1, all this slide. So VRF1 is configured with import root target 10:20. So this entry will go to VRF1 routing table inside the VRF1, and this entry will go to VRF2 routing table. And this is the rep inside, because as we mentioned earlier when we were discussing the VRF, it consists of a rep, a routing table, and Ceph forwarding information base. And the Ceph forwarding information base comes from the routing information base. So let's think about the upper VRF, VRF1, where this root or this prefix specially will be added to this routing table because of the root target. So it will be learned from BGP, and the root distinguisher is removed because we don't need it anymore. BGP started to differentiate between the two prefixes, and once they are redistributed into IGP, the RD is not important. The RD and RT works with multi-protocol BGP. So in this step 4, the prefix is learned in VRF1 routing table, and the next hop will be the VPN v4 neighbor that was assigned inside this entry. The next step is to constructing the Ceph forwarding information base from the routing information base inside VRF1. How this will be accomplished? The prefix will be stored as a prefix. The out label contains two labels. The inner label that was assigned by BE2, will be stored here as an inner label. And the outer label that was chosen by BE1 from the label information base will be stored as an outer label. Which one of these advertise the best label is P1, because it comes from here. So this will be the next hop, and this serial 2/1 output interface will be taken here, and then the Ceph forwarding information base is ready. So when BE1 receives unlabeled packet destined to 10.3.3.0 that comes from an interface associated with VRF1, it will check its Ceph forwarding information base and then will assign an outer label 10, an inner label 17, and send to the next hop P1 out of serial interface serial 2/1. Similarly for VRF2, the second entry here, because of the root target, it goes to VRF2 routing table learned by BGP to the IGP, and the next hop is the neighbor VPN v4 router, which is provider edge 2, and then this prefix will be stored inside the Ceph forwarding information base. The out label comes from the label information base, because as you know, the label information base feeds the MPLS label forwarding information base and the safe forwarding information base. But as we are discussing the safe forwarding information base in this slide, this out label, as long as it was chosen as the best label, will be stored as an out label for the safe forwarding information base, and the VPN label came with the BGP update will be stored in the safe forwarding information base as an inner label. The next hop came from the label information base as it advertised the best label, and the output interface as well will be P1 out of serial to 1. Now VRF1 has a safe forwarding information base, and BE2, as we discussed in the previous, not the previous one, previous one, how BE2 constructed the MPLS label forwarding information base for VRF1, VRF2, and the MPLS unicast IP forwarding as well. Last thing to discuss here will be the penultimate hop popping feature that Mpls Vpn uses. Actually, it's not a data plane. Oh, yes. So what is this feature that Mpls Vpn uses? It uses the label switched path and determine which is the last MPLS hop and call it ultimate MPLS hop, which is the last hop inside the MPLS cloud. The label switch router before this provider edge or this last hop, which is P1 if it was chosen, will be called penultimate MPLS hop, and its description is next to the last based on the label switched path to this specific prefix. So when the feature that will be used by Mpls Vpn, which is PHP, will work as like that. When a next to last or penultimate MPLS hop or label switch router receives a labeled packet, it will remove the outer label. Why? To save some work for the last hop or the ultimate hop, MPLS hop. Instead of doing two lookups, it will do only one lookup because it will receive a packet, a labeled packet with only one label. So this MPLS router will remove the outer label because it is penultimate MPLS hop or MPLS label switch router, and this last hop or ultimate MPLS label switch router will do only one lookup for the inner label, or for it will be only label, and it will check its MPLS label forwarding information base and find a matching label, a matching entry, and take a decision or action removing the label in this case, and send an unlabeled packet out of serial 2/2. So actually it is not MPLS unicast IP forwarding. It's Mpls Vpn. So in this slide we will make a configuration for this example. As we discussed most of the slides we use the same topology, two customers or two enterprises, enterprise 1 and enterprise 2. Each one has two sites, site A and site B for enterprise 1, site A and site B for enterprise 2. And site A for enterprise 1 will use 192.168.1.0/24, and similarly for site B, for site A for customer 2, and for site B for enterprise 1 or customer 1, we will advertise this prefix, and there is an overlapped prefix here, so you will know how Mpls Vpn will differentiate between these duplicate prefixes and these duplicate prefixes. All what we want to do here, we want enterprise 1 site A learns about routes in site B of enterprise 1 and vice versa, and only from site or from enterprise 1 sites only. And for enterprise 2 sites, they will learn about routes from each others and only from enterprise 2. No learned routes between enterprise 1 and enterprise 2, or if there is no shared site here that enterprise 1 can learn routes from, and so on. We will just make connectivity between these two sites through Mpls Vpn and connectivity between these two sites through Mpls Vpn, and these two enterprises uses duplicate private IPv4 prefixes. So let's start the configuration. Actually, I prepared this topology. It is exactly as the suggested example here. All what I did, I configured the interfaces for each router with IP addresses as suggested in this example. All what I did to all these routers is configured the IP addresses for interfaces. For example, customer edge 1 site A has one serial interface, serial 2/0, and loopback 0. So I configured these two interfaces, and the IP addresses for serial 2/0 is 20.1.1.1. So to configure Mpls VPN, we will do the following. First of all, let's open the console of each router. We will start by configuring EIGRP inside the Mpls cloud as the IGP that we are going to use inside the Mpls cloud. So let's go to BE1 and configure EIGRP 200 and advertise the networks inside the Mpls cloud. We will start by 30.1.1.0.0003 and network 40.0.1.1.0. We will advertise this and this. We will enable EIGRP here and here. We will not enable EIGRP 200 between the provider edge 1 and the customer edges. So now we configured EIGRP one thing, we need to advertise the loopback interface, because for each label switch router or MPLS router, I use loopback 0 with these IP addresses: 1.1.1.1 for provider edge 1 and 2.2.2.2 for provider 1, and so on. So for provider edge 1, I'm going to advertise this IP address. And just to show you the configuration, let's first show IP interface brief. I'm configuring these IP addresses as in the figure, and this is the loopback interface. And for the running configuration, IPsec is enabled by default. As you can see, only IP addresses for serial interfaces, and this is the EIGRP that we configured, nothing more. All other routers are the same, only IP addresses for the serial interfaces. So now let's go to P1 to configure EIGRP. We will advertise network 30, or we will enable EIGRP on interface serial 21. And then neighborship will be yes, and then subnet 50.1.1.0 and 70. In addition to the loopback interface, because it will be used by BGP for the neighborship, BGP neighborship, because we will update the source, and it will be used by LDP when forming LDP neighborships. Let's go to B2. Configure EIGRP router EIGRP 200 network 40.1.1.0. So it will 0. Sorry, not the 0, the 3. Then network 70.1.1.0 0.0.0.3. Then network 60, and eventually the loopback interface 3.3.3.3 0.0.0.0. We will advertise it via EIGRP. Let's go to provider edge 2, configure EIGRP. .1.1.0.0.0.3. So it will make neighborship with P1, and then 60, and this will perform neighborship with P2. For now, we configured IGB or EIGRP inside the MPLS cloud. The next step, we are going to configure BGP inside the MPLS cloud. So BGP neighborship between all these 4 routers, MPLS routers. So we will use full mesh for IBGP. Let's start by B1. Configure BGP router BGP 200. And for simplicity, because we will configure full mesh, we will use peer group. So we will configure, let's say, autonomous system 200 group, peer group. And then the neighborship inside this group will be with remote autonomous system 200, so all are IBGP. And then we will update the source for loopback 0. Then we will configure neighborship with P1 peer group and with B2 and eventually with provider edge 4. Sorry, provider edge 2. This is the IP of the loopback 0 in PE2. And it is advertised by EIGRP. Let's exit this and go to P1. But let's keep this and go to P1 so we can copy the first router BGP 200. We will take neighbor this and we will take the same autonomous system because they are all inside the autonomous system 200. So all neighbors inside the autonomous system means they are IBGP neighbors. We will update the loopback interface, the source, update source with loopback 0. And then the neighborship will be with, this is router P2 and then BE1 and then 4.4.4.4 BE2. We can see that the BGP neighborship started to be established and becomes up and up. Then let's go to B2. But for P1, before we forget, let's save the configuration. Then for B2, we will configure BGP similarly. Neighbor, this one, and remote autonomous system 200, and we will update source with loopback 0, and then take the neighborship with these neighbors. This is P1, this is PE1, and this BE2. Last thing, to configure BGP or IBGP on BE2. Router BGP 200. Let's take the same commands. Remote autonomous system 200. Neighbor update source loopback 0 for this peer group, and then neighbors with this group, with these neighbors that will use all these commands for these neighbors. Instead of configuring each one for each neighbor, we use this peer group. So the first neighbor, IBGP neighbor, will be BE1, then P1, then yes, then B2. Now we configured BGP. Let's confirm neighborship is not up. Show running section EIGRB. I think I forgot to advertise the loopback interface through IGB. That's why the neighborship is not up. So let's go to router EIGRB200 and then network 4.4.4.4.0.0.0.0. Yes. Let's save the configuration. Let's save the configuration on P1. And P2. One last thing I want to do for PGP, I want to advertise the networks so we can trace the route successfully and we can ping all the routers. So here mask 255.255.252 and network 40. Then for P1, let's copy first the command. And for P1, we will advertise 70 and 50. And for B2, we will advertise 60. So PE1 advertise this and this, P1 advertise this and this, P2 advertise this. No more networks to advertise. So let's save the configuration and check the Bgp table. Yes, almost all. Some are learned from other neighbors, are best. Okay. Okay. Now we configured EIGRP inside the MPLS cloud, and we configured BGP inside the MPLS cloud. Last step, let's configure MPLS inside the service provider cloud. And as you see here, MPLS will be enabled in the green interfaces, these green lines only. So let's start by PE1. Let's first, IPsef is enabled, so we don't need this command, but just for making sure. Some routers may have not IPsef enabled by default for IPv4, so you should enable it so you will be able to configure MPLS. Now let's go to serial interface 2/1 MPLS. But let's first, I want to configure something. MPLS label range for PE1. Let's use from 100 to 199, and then the LDP protocol, the label protocol is LDP, of course, by default. So now let's enable MPLS on interface serial 2/1 by using MPLS IP, and enable interface serial 2/2 MPLS IP. One last command I want to add to make sure that LDP will use the LDP ID of the loopback interface 0. So we will type the command mpls ldb router ID loopback 0 and force it. Let's go to P1. We will configure, for example, MPLS label range for P1, let's say from 200 to 299, and we will use this command for the LDB ID, and then we will enable MPLS on interface serial 21 MPLS IP, and then interface serial 2/2 MPLS IP, interface serial 2/0 MPLS IP. Save the configuration. Let's save it here as well. Now we will configure B2 using the same commands here. MPLS label range 100, 200, 300 to 399. We will use the same commands as we did with P1, and then enable MPLS on interface serial 20 MPLS IP, interface serial 2/2 MPLS IP, interface serial 2/1 MPLS IP. Then BE2 MPLS label 400 499, and then we'll force the LDB ID, and then enable MPLS on interface serial 2/0 and interface serial 2/1 MPLS IP. Very good. If you want, for example, on PE2 to check MPLS label range, okay. If you want to show MPLS LDB neighbors, 2, very good, with P1 and B2, 646 for LDB. Okay. Then we need to configure. By the way, till now there is nothing new in the configuration other than the configuration we configured with MPLS unicast IP forwarding. From this moment, the configuration will differ a little bit because we will configure VRFs, and we will do redistribution between the IGB into BGP inside the address family. So let's start by creating the VRF, and the VRF is configured on the provider edges only. So IBVRF, let's call it VRF1 for customer 1, and as we discussed, it should be configured with a root distinguisher. We will write the autonomous system number, because if you will see here, you can use this format or this format, but I prefer this format. So 100 because it is for customer 1, and any numeric or integer value, let's say 70. And then let's configure root target. We have two options here to either configure import, export, or we can configure a value directly and it will be used for both import and export. But for this example, I want to use different root targets. So let's start by export. We will export 100 and value, let's say 30, and we will import with value 120. You should keep these values because we will use the opposite on BE2. So now we configured VRF1 because the VRF requires a name and root distinguisher, and configure the root targets. And because we are connecting customer 1, side A and side B to each others only, we use these root targets to be updating the other VRF on BE2 only. We will not update any other VRFs. So IB VRF2, let's create VRF2, and we will give it root distinguisher 300, the autonomous system for customer 2, and let's use the value 90. Root target, export, let's give it 340, and import 330. Now we configured the VRF. Let's save the configuration. What's next is that we should enable the VRF or associate the VRF to a specific interface. So customer edge 1 for site A is connected to the provider edge 1 through provider edge 1 serial 2/0. So let's go to serial 2/0 and associate the VRF by using the command ibvrf forwarding vrf1. This will remove the IP address of the interface, so we will need to reconfigure the IP address of the interface. So let's hit enter. Okay, and then IP address 20.1.1.2 255 255 255 252. Similarly, with interface serial 2/3 IB VRF forwarding VRF2 IP address 100.1.1.2 255 255 255 252. I think it's not shut down, but just to make sure. Let's save the configuration. Now we should do the same on BE2. Let's go to BE2. Create VRF, we will call it, let's say VRF1 because it's for customer 1. You can call it whatever you want. But the most important is that the root targets should match what is inside in BE1. So root distinguisher here, we will use 100, and what is the value we used in BE2, BE1, sorry. We use 170. We can use the same or different root distinguisher. So let's use root distinguisher 80, 100:80, and root target. Let's first start by import. We will take the export here to import here, the same value. And root target export, same as import there, as we demonstrated in the slides. So roots from BE1 VRF1 will go to BE2 VRF1 as well, and vice versa. Now let's go to IB VRF VRF2 root distinguisher 300, and we used here 390, let's say 300 100, and root target import, let's take it from the export, and root target export, same as the import here. Now let's associate the VRFs to the interfaces 2/2 IB VRF forwarding VRF 1 because serial 2/2 is connected to customer 1. So we created VRF1 for this customer. Okay, let's reconfigure the IP address 80.1.1.2.255.255.255.252. Similarly, with interface serial 2/3 IP VRF forwarding VRF2 and then IP address 90.1.1.2.255.255.252. Let's save the configuration. I just wanna show ID interface brief. Interfaces are up. Okay, now we configured VRF on BE1 and BE2 with the root distinguisher values and root targets values. Now we should configure customer edges. Let's start by customer edge 1. All what we are going to configure here is to configure router EIGRB 100 and advertise network 192.168.1.0.255 and network 20.1.1.0. So neighborship will be with PE1 address family for or EIGRB instance specific for autonomous system 100. So let's advertise these networks. No more configuration on the customer edge. Just enable EIGRB on the interfaces, and then we will do the same here. But I want to make sure which autonomous system I use. Yes, 100. For customer edge 2 site A, we will use router EIGRB 300 because this is the autonomous system. We will advertise the same network 1.0.0.0.255 and then network 100.1.1.0.0.0.3. Let's do the same for CE1 B. Router EIGRB 100 network 10.3.3.0.0.0.255 and network 80.1.1.0.0.0.3. Now we enable EIGRB on the customer sites except the last one. Router EIGRB 300 network 10.3.3.0.255 network 90.1.1.0.0.0.3. Until now there is no neighborship because this is in autonomous system and the provider edge in another autonomous system, and we are not advertising these routes inside EIGRB for serial 2/2 and serial 2/3. But let's go to PE1 and then we will go to router EIGRB 200. Inside this router EIG 200 we will configure address family IPv4 VRF. It means that for VRF1 and autonomous system 100 make a neighborship with the customer edge router. As you can see, we are not making EIGRP neighborship between autonomous system 200, but inside it address family that is associated with VRF1 and autonomous system 100. So inside this EIGRP instance or address family, we made network EIGRP neighborship with this customer, so they can exchange routes learned from the customer site. Similarly, we will go to address family, IPv4, VRF, VRF2, autonomous system 300, network 100.1.1.0. Exactly. Now a neighborship with customer 2 site air edge customer edge router. Now let's save this configuration. And if you want to check on PE1 where this prefix 192.168.1.0/24 stored, you can check VRF1. So if you do show IP root VRF1, as you can see, this customer root learned by EIGRP. Similarly, you can check VRF2 and you will find the same subnet, but this is this time from customer 2. So each route belongs to the dedicated VRF. Let's do the same from the other side, BE2. And configure router EIGRP 200, address family, IPv4, VRF, VRF1, autonomous system 100, network 80.1.1.0, 3. Exactly. Address family, IPv4, VRF, VRF2, autonomous system 300. By the way, some iOS, Cisco iOS versions, you configure the address family until VRF2, and then you configure autonomous system 300 inside the address family interface EIGRP subcommand or address family subcommand. So you see here autonomous system, but this version supports the autonomous system in the address family command. So we'll say here inside network 90.1.1.0, 3, neighborship should be formed. Exactly. Let's save. Show IP root VRF, VRF1. As you can see, it learned about subnet 10.3.3.0 via EIGRP. If you will check VRF2 routing table, you will find out the same subnet from the customer 2 customer edge router. If you will check show IP root, the global routing table, you will not find these routes 10.3.3.0. Why? Because they are stored inside the specific VRF, not in the global IP routing table. What is next? Now we published or advertised the customer routes to the provider edges via EIGRP. Now we should redistribute, if we want to explain it here. Let's say this is the MPLS cloud. This is provider edge 2, provider edge 1. It learned via EIGRP about customer routes. Similarly, provider edge 2 learned from customer sites via EIGRP the customer routes. Now let's think about PE1 should advertise, or sorry, should redistribute from the EIGRP instances into BGP. And then there we will redistribute from BGP into IGP. And for BE2, we will redistribute from EIGRP into BGP. And then here from BGP to EIGRP between the customer sites. So the routes will be learned, and Mpls Vpn will have almost done for the configuration, except only one command to enable Mpls Vpn between these two provider edges where the customers are connected. Let's continue the configuration. We will start by PE1. So we will redistribute from EIGRP 100 and 300 instances, our address families, inside BGP 200. So router BGP 200 address family IPv4 VRF VRF1. What should we do? We should redistribute EIGRP 100 into BGP. Then address family IPv4 VRF VRF2. We should redistribute the EIGRP learned routes into BGP. Now we did the redistribution from IGP to BGP. Let's go to the other side, BE2, to redistribute from BGP into EIGRP instances. So we will go to router EIGRP 200 address family IPv4 VRF VRF1 autonomous system 100, redistribute BGP 200 with metric. Let's give any values. 255 255 1500. Let's do the same for the other VRF address family IPv4 VRF VRF2 autonomous system 300, redistribute BGP 200. Let's use the same values. Now we redistributed from BGP into EIGRP instances. Now let's save the configuration. From the right hand side to the left, let's redistribute what is learned from EIGRP into BGP. So router BGP 200 address family IPv4 VRF, VRF1, redistribute EIGRP 100. Similarly, address family IPv4, VRF, VRF2, redistribute EIGRP 300. Let's save the configuration. Go to PE1 to redistribute from BGP into EIGRP. So router, we want to from BGP into EIGRP. So EIGRP 200, address family IPv4, VRF, VRF1, autonomous system 100, redistribute BGP 200, metric, and similarly redistribute into VRF2, address family IPv4, VRF, VRF2, autonomous system 300, redistribute BGP 200, and metric 255 and MTU 1500. Till now, there is only one thing is missing: to configure Mpls Vpn between BE1 and BE2. So to configure the Mpls Vpn between BE1 and BE2, let's go to router BGP 200, address family VPN v4, and then say neighbor what's BE2 4.4.4.4 and activate. Let's do the same with BE1, with BE2, sorry. Router BGP 200, address family VPN v4, neighbor 1.1.1.1, activate. Now let's check something. Let's go to customer edge 1 and ping 10.3.3.50. It can go, but let's check the root, trace route 10.3.3.50, because which one, this one or this one? We will check here. We are sure that it will be customer 1 because we configured the route targets to from customer 1 side to customer 1 side and vice versa. And as you can see, the route is to BE1, then B2, then provider edge 2, then customer edge 1 side B. So this is inside B of customer 1. Let's go to customer edge 2 site A and ping the same network. It's reachable. Trace the route 10.3.3.50 and look for the difference. It went to provider edge 1, then provider 2, then provider edge 2, then customer edge 2 side B. This is customer edge 1 side B. Let's check the labels, and as you can see for here, when provider edge 1 received unlabeled packet and send it to provider 2, it send it with two labels. This is the outer label and this is the inner label or VPN label. Then B2 send a packet labeled packet, but because Mpls Vpn has the feature penultimate hop popping, this P2 is the next to last or penultimate Mpls hop, so it removed the outer label and left only the inner label. Then when BE2 received this labeled packet, it removed the label, this label, and sent to customer edge 1 site B unlabeled packet. If you want to check the tables and how Mpls VPN works inside the Mpls cloud, let's start by provider edge 1. First of all, let's check show IP Bgp VPN v4 all. This is the Bgp table. This is the Bgp table for BE1, and as you can see, this is for VRF1 with root distinguisher 10.70, and this for VRF2 with root distinguisher 300:90. Because of we didn't use the same root distinguishers for each customer site, some, for example, look here, this root learned by from BE2 for 4.4.4 and with root distinguisher 100:80 and no associated look, if we use the same root distinguishers for both BE1 and BE2 VRF1, you will not find this. Why? Because this root distinguisher, no, there is one moment. The root, let's check from the root target point of view. BE2 show running. The VRF here, VRF1 has root distinguisher 100:80 and the root distinguisher for VRF1 has 170. So when BGP advertised the BGP table from BE2 to BE1, it advertised with this root distinguisher, but the root target inside VRF1 export from this, and this entries in the BGP table with root target 120 should be stored inside VRF1 because of the import root target 120. and this VRF has root distinguisher 100:70. So root distinguisher 180 has only these roots came along with root distinguisher 180. But what is advertised inside VRF1? If it has the same root distinguisher, you will not see this, and you will see here 80, 180, and the roots are imported to this VRF. So if this command show Bgp Vpn v for all just tells you that what is the Bgp table that will be advertised to the Mpls Vpn neighbor via iBGP. As you can see, most of the learned routes are by iBGP, and the other redistributed routes are considered coming from outside of iBGP or eBGP. Not eBGP, it's from redistribution. So this is the BGP table for each VRF. Let's show BGP VPN v4 unicast all neighbors. What this gives you, as you can see here, I just want to show you that all the neighborship, the VPN neighborship between BE2 and BE1 are with remote router ID 1.1.1.1, which is BE1, and the BGP state is established. This is called Mpls Vpn between BE2 and BE1. Even they don't have a direct connectivity, they just have iBGP neighborship because we used full mesh, and the VPN is created between BE2 and BE1. If you will use this command on B1, for example, no neighbors, because no VPN v4 neighbors. Mpls VPN between the provider edge routers. Next, let's check from BE2 side when it received 10.3.3.0 from customer 1 side B. What was the action taken? Let's check the MPLS label forwarding information base for VRF, or you can hit enter, see all the table. But if you want to see for a specific VRF, but let's see here, because this command show all the MPLS label forwarding information base inside B2. It assigned for this prefix that came from serial 2/2, means from customer 1. It assigned a local label 408, and this is the label should be the VPN label or the inner label. If you want to make sure, go to CE1, trace route here, and you see the inner label is 408. For the other prefix that came from customer 2 side B, serial 2/3, the local label, which will be used as the VPN label or the inner label, is 409. Go to customer edge 2 and you will find out that the inner label is 409 as assigned by BE2. Now let's check LDB to see the outer label. Let's go to BE2, show Mpls LDB bindings, and you see you will not find the prefixes from the customers because they are stored in VRFs, and this is the label information base for BE2. It has only the EIGRP prefixes, learned prefixes, learned by the IGP. So what we are looking for, we are looking for this one because it will be advertised by LDB, and as you can see here, the label, local label, nothing for it. But if you will check, it was advertised without a label, just for the PHP feature perspective, from the PHP feature perspective. Let's check B1, or let's check B2 because B2 was chosen for this route. Show Mpls LDB bindings, and then we will find out that B2 assigned a local label 302 and it advertised. Let's clear this. BE2 advertised 4.4.4.4/32 without a label via LDB to B1 and B2. Now B2 assigned a label 302 as a local label and advertised to PE1. So the label here is 302, and the label from P1, so Mpls LDB binding, you can see here 4.4.4.32. The label, local label, is 202, so it advertised this prefix to PE1 with label 202. If you will check BE1, label forwarding label information base, show Mpls LDB binding for 4.4.4.4.32, you will find out that it received 202 from P1 and 302 from B2. Which one it's choose? Check the Ceph table, show IBCEF VRF. Let's check for VRF1. But let's do for 10.3.3.0 255.255.255.0, and you will find out that the Ceph forwarding information base on PE1 choose 202 as an outer label and 408 as an inner label. This was assigned by PE2 408 as a VPN label, and you can see here as an inner label or VPN label, and two labels came from B1 and B2 as an outer label because it's LDB labels. Now those two labels are in the FIB because of EIGRB has the same metric from BE1 to BE2 through B1 and B2. If you want to have only one, let's do something for EIGRB between BE1 and B1, for example. We will decrease the delay interface serial. I just want to make sure one route will be added. Interface serial 2/1 delay, let's say 100, and go to P1 2/1 delay 100. Now the metric will have different values for all subnets. We're just doing this for the purpose of choosing one route or prefer a route over another by EIGRB, and then by LDB. One label will be best. So let's check PE1 again. We will do this command, and you can see now that BE1 preferred the 202 over 302 because from EIGRB P1 has a better route. So this label will be preferred from the label information base and will be stored in the IB in the safe forwarding information base of PE1 of VRF1. Now when PE1 want a packet will be destined to 10.3.3.0 and come from customer 1, it will attach this label as an outer label and this label as an inner label and send to P1. P1 will receive a labeled packet. What it should do, it should check its MPLS label forwarding information base. So let's go to P1, show Mpls forwarding table for all. Let's check 4.4.4.4 because this is the Bgp neighbor with PE1. This is the local label, and this local label, if the received packet from PE1 came with an outer label 202, the action is pop, remove the label, and send to serial 2/0 out of serial 2/0. Serial 2/0 towards to BE2. Let's go to BE2. When it receives a labeled packet, it will check the MPLS label forwarding information base. Show MPLS forwarding table. Let's check when a packet comes with, as you can see here, B1 remove the label, remove this outer label. Let's make it clear from all perspectives, from all routers, so everything will be clear. here P1 BE1 attached 202 as an outer label and 408 as an inner label. When B1 receives a labeled packet with an outer label 202, it will remove it and leave the inner label and send the labeled packet to 2/0, which is BE2. Now BE2 received a labeled packet with a label 408, 408 from the MPLS label forwarding information base. The action will be remove the label and forward this packet outside of serial 2/2 to customer 1. Now MPLS is configured and works. So to this we come to the end of this video. I hope it's been informative and thanks for watching.